This is part 2 of Biostratigraphy. Again, this is for 3 of 104C at USF. This is Sarah Sheffield. All right, so we're going to pick back up with practical applications of biostratigraphy. Besides figuring out age, we can actually also estimate the rate of deposition using biostratigraphy. So if you take a look at column A and column B, we see a series of fossils, fairly similar, right? I was about to say they're from same sequence, just different locations. So how do we know which one deposited faster? Well, let's take a look. We can correlate logs, we can figure out how fast things were by plotting them. So if we take a look, if x and y was equal rates, we actually see that location A was depositing a little bit faster in this particular time. So that's one cool thing that we can do, and you'll get more practice with this in a little bit when you start your in-class assignment. As a reminder, correlation lines aren't always straight. So if we see here, there's something going on where there's just a flat line here right in the middle of location X. So this here has a steady deposition rate, but something is happening where there's no deposition here. What do you think that could be? You guessed it, it's an unconformity. Excellent. So there was a hiatus of sedimentation, and then we see a resumption of that same sedimentation. So why that could happen are for a whole bunch of different reasons, but this is how you would indicate a unconformity if you were doing one of these as well. So fossils and plate tectonics. One really cool thing is that the deformation of fossils can help you work out what was going on during the folding of the larger rocks, all right? So fossils can be really important in dating orogenies because when we have orogenic events, we can see a lot of metamorphic deformation of rocks, which can mess up our absolute ages. However, you cannot change the age of this brachiopod by squishing it, right? Because brachiopods are really good index fossils through most of the Paleozoic. And they're really going to be important for lots of places like the Tennessee Smoky Mountain areas, where we have lots of brachiopods and we have lots of deformed rocks. So they're really important there. So the best structural geologists can identify brachiopods because it can tell you a lot about the ages of the rocks. Pretty cool, right? So we can tell what's going on with stress and strain, what direction things were being folded in, things like that, just by looking at the brachiopod. So biostratigraphy isn't the only answer here, right? It doesn't solve all of our questions concerning stratigraphy and time in the geologic record. First, we can't really get absolute dates very easily. So why can't we use radiometric dating reliably on sediments and living things like fossils? Well, there's a couple different reasons for that. So sediments do often contain minerals that have the possibility that have the ability to be radiometrically dated. But remember that sedimentary rocks are formed from the reworking of other rocks. So it can be really difficult to tease out where something came from. It's not entirely reliable. Reworking. Fossils can be eroded out of a layer and redeposited at a later date. How might we be able to tell? Well, there might be unconformities nearby. There can definitely be other sedimentary structure signatures that might tell us. A famous example of this is not too long in the distant past, there were some dinosaur bones found in the Cenozoic, right after the base of the Mesozoic and Cenozoic boundary, the KPG extinction, Cretaceous-Paleogene. And a lot of people were like, oh my gosh, dinosaurs made it through to the Triassic. They didn't, all right? That boundary still holds firm. What had happened is some of those bones had been reworked up to a later age. So this can be really important to know. The senior ellipse effect. This is a really cool one. So essentially, the idea is, and I'll explain why there's awkward photos of me here in a second, first and last appearance dates of fossils are not the true last and first appearances of the species. As you can imagine, the fossil record is vast, but it is also vastly incomplete, meaning the chances that that trilobite you found is the last surviving specimen of its species is exceedingly rare, and frankly, you and I will never know if that's the truth. All right? So social media is a really good analogy here. The first and last photo of yourself on Facebook will be after you were born, presumably. I guess now that maybe doesn't work because Facebook has been around for a lot longer now. Whoops, that analogy failed. I'm getting old. All right. And presumably, the last photo of you will not be the one as you are dying. All right. So they're just snapshots that show relative time, but not the first and last appearances. Does that make sense? So seeing your ellipse effect, here we go. How this works is here's the extinction event shown in stars right here. All right. Here's the last observed fossil occurrence. It comes long before the extinction event. What this can do in the fossil record is it makes abrupt extinctions look more gradual. So for, again, the KPG example, dinosaurs, it looks like there was a much more gradual extinction leading up to it. And in other creatures too, like forams. Forams show a gradual extinction leading up into the KPG. But when we actually look at the data and we remove some of the biases, we can see that there was an abrupt extinction event, the asteroid impact, for example. So here is what it looks like. All right. So essentially, the more fossils we have, the better approximation of the true extinction event and what can kind of reduce that senior ellipse effect. So if we only have a couple fossils, we're probably not going to get a great answer, which is another reason why we need to be exceedingly careful about the data that we're working with and to estimate and understand the biases we might be introducing into our science. Okay, so another point with the senior ellipse effect, with the social media example below, really, or above, the fossil record is incomplete and biased towards certain environments. For example, on social media, we're more often to see the fancy food people are eating at restaurants or vacation trips. Actually, it's 2020. We're not seeing any of that right now. That's a bad joke. I'm so sorry. But in general, it doesn't show a complete picture of what's actually going on. So in the fossil record, we most often see shallow marine organisms, not terrestrial organisms, though we know things were living on land. We see things with hard-shelled pieces like crabs and trilobites, not necessarily jellyfish as often, even though we know we have jellyfish fossils as well. This last point here is the Lazarus Taxa. Lazarus Taxa gets its name from the biblical character Lazarus, who came back from the dead. And these fossils are called Lazarus Taxa because we thought they were extinct, but it turns out they're not. In recent news, the elephant shrew, who has been thought to have been dead for decades, was just discovered running around an area like 2 days ago. You should check it out. Stop what you're doing. Yes, stop the lecture and go Google a picture of the elephant shrew. So cute. So let's talk about the coelacanth. Very strange looking. The coelacanth it was around at the time of the dinosaurs, all right, the non-avian dinosaurs in the Mesozoic. We have images of it. It's really important for us to understand how the first fish walked on land. The coelacanth is the sister group to the things that will start to crawl up onto land, like Tiktaalik, the walking fish. And this thing here can actually push sediment out of the way. So if you imagine you're like paddling a little bit, I'm actually doing this right now, but obviously you can't see me. It actually pushes sediment out of the way on the sea floor to kind of traipse along it. So we actually have a model of how the first organisms could have walked on land, how the first vertebrate organisms, I should say. But we thought they went extinct. So a couple of years ago, and by a couple of years ago now, I mean quite a few decades ago, one was caught on a fishing expedition, and it turns out they're still alive. So that's the Lazarus Taxa. We thought it was dead, and it turns out, well, hello, still alive, not extinct yet. It's actually happened quite a few times in our paleontological history. Now, the last problem with biostratigraphy does not work in the Precambrian very well. Why? Well, for the majority of our time on Earth, there was no life, which means biostratigraphy, of course, cannot work under any circumstances. And then finally, once we start getting fossils that can be easily identified and traced, many of them are not entirely globally common and they're not easily identifiable. So really, biostratigraphy works only in the Phanerozoic, I would say. All right, so these are the review topics that I would like you to focus on. So these are some of the questions that I would find more important than others. So check these out. Ask if you have any questions, and I will see you for the in-class assignment in just a little bit.